Going over the review sheet today, we'll start with problems 1 through 4. Find the indicated nth root. So we're applying this root to the given number. So number 1, we're looking at the fourth root of 20,736. So we need to see what number times itself 4 times is this here. We can leave that cracked. Now the first thing I would do is take the 30xs. Most of this we can do on the 30xs. Be helpful if I actually remember the number, 20,736. Type it in and we get 12, which is really telling us that 12 to the fourth power is 20,736. But since we applied a fourth root to it, an even root to it, we do have to put a plus or minus. Because negative 12 to the fourth power is also positive 20,736. So this actually gives us plus or minus 12, positive or negative 12. And we have to put that fourth, or that plus or minus, because we took an even root. Any questions on number 1 before we look at number 2? Number 2, we're looking for the ninth root, since n is 9, of 512. We're trying to figure out what times itself 9 times is 512. Again, first thing I would do is just plug the ninth root of 512 in the calculator, and it tells us it is indeed 2. Which means, if we wanted to verify that, we could just do 2 to the ninth. We can go the other direction. And 2 to the ninth is indeed positive 512. Now this one we don't put the plus or minus, because negative 2 to the ninth power is negative 512. We need it to be positive, not negative. Where in the even root case, we still got a positive number. So an odd root, we don't put the plus or minus. Even root, we do. And if you're not sure, we can check it just like we did. Check the positive, check the negative case. If they both give us the same number, we need the plus or minus. If it doesn't, we do not. Number 3, we want to take the 14th root of 16,384. And just like with the first few, I'd grab the calculator. 14th root of 16,384. Lo and behold, it is 2. Now, because it is an even root, we do have to put the plus or minus. Because 2 to the 14th power is indeed positive 16,384, the value we started with for A. If I check negative 2, we also get positive 16,384, the same value of A. So we need both the positive and negative case, so we have to put the plus or minus. Well, at this point, might as well go on and do number 4. 5th root of 1,024. Fifth root of 1024 is 4. So we're saying that 4 to the 5th is 1024, and it is true. However, we would not have the negative case because we took an odd root, because negative 4 to the 5th power would give us negative 1024, not positive. It's just going to be 4. Questions on this here? Evaluate each expression. And with most of these expressions, especially on the test, the first thing I would try to do is just plug it in. with any of them. 8 to the negative 2/3. And if it gives us a nice rational answer, we're going to use it. If it doesn't, and it's not asking us to approximate, we would have to actually work this out or simplify it as far as possible. If it starts off with rational exponents, we're going to leave it in rational exponents. If it gives us it in radical form, we most likely want to stay in radical form. We don't want to switch between the two, at least for the general purpose. Number 6, 1/4 to the negative 5/2 to the 3rd to the 6/5. 1, 2, 3. 1/4 to the negative 5/2 to the 3rd, parentheses, to the, now since it gave us that checkered pattern, what it's saying is it doesn't have enough space, it doesn't have enough memory to keep going. So there's one of two things we can do. One of them, let's just actually figure out what we have so far. Let's see here, didn't like that. Okay, 32,768. So really all we've done is figured out what's inside here. 2,768. We have not applied the 6/5 to it. So one way we can do it is we can figure out as much as we can. So 1/4 to the negative 5/2 to the 3rd is 32,768. Then we can take our 32,768 and put it to the 6/5, which is 262,144. Is our final answer. I'm curious, but I have a feeling this might work because 3 parentheses. Instead of 1/4, I'm going to write it as 0.25 to the negative 5/2 to the 3rd to the, let's see here, 6. Won't let us do another fraction, but we can divide 6/5, giving us 262,144. Or we can take it bit by bit, because the first thing we have is, let's make sure I'm not doing 14, 1/4 to the negative 5/2. Then we put that to the 3rd. And then we put that to the 6/5. So we can take it bit by bit or break it up as we need. Different ways we can do it, different ways we can get to the answer. But the answer is still 262,144. Even the last one, 1/9 to the 3/2.
Is he in this class?
He is not.
Sorry.
You're good. 1/9 to the 3/2 is 1/27. And we can do it for the last one here, and if we plug 16 squared to the negative 1/4, it tells us 1/4. Because if it's giving us these nice rational answers out of the calculator, keep using it. If it doesn't, then we actually need to calculate it out and use our simplifying steps. 9, 10, 11, or 12, which one do we want to look at? 12. Now this one here, evaluate each expression and round to the 4th decimal place. It is not asking us to keep it in radical form, so we could grab either calculator. And number 12, the 5th root of 8 to the 8th. 27.85761803. It asks us to round to the 4th decimal place, so I look to the 5th, which is 1, telling us that we round down, telling us that this is approximately 27.8576. And that's it. And really, for all of these here, we can do the same thing. 6 root of 974,231 is 9.95658. So when we round, we get 9.9566. Just plug it in and round to our decimal place. 816 to the 1/9. No different. 816 to the 1/9 is 2.1063. And lastly, 2 to the 4/5 is 1.7411. Plug it in, round to our appropriate decimal place. Questions on this here? Are you ready for the next few? (13 through 16), simplify each expression using the property of rational exponents. So again, 6 to the 3rd to the 1/4. The 3rd. Thank you. So 6 to the 3rd to the 1/4. We are given this irrational decimal, which tells me the calculator is not going to simplify it for us. We've got to simplify it ourselves. One of our properties of exponents, powers of powers, multiply. So this is the same as 6 to the 3 times 1/4. Well, 3 times 1/4 is 3/4, telling us 6 to the 3/4. And really, at this point, there's nothing else we can do. No negative exponents, no like bases. This is it. Now, if I wanted to, all right, guys, focus in. If I wanted to check and make sure that those are the correct expressions or equivalent expressions, we can plug it in. We see that 6 to the 3/4 and 6 to the 3rd to the 1/4 both have the same value. So that means they are equivalent statements. But this is our final answer. We're not going to write it as a decimal approximation because it told us to simplify, not round. Questions on any of this here? Because we could do the next one by hand. 48 over 27, I could grab that calculator and see 48 over 27 if it reduces, if it simplifies, 16/9. So that is helpful because since they are being put to the same power, we can remove that negative 1/2 from both terms, giving us 48 over 27 to the negative 1/2, all to the 4th power. At this point here, I'm going to do two things at once. One, because you don't have a whole lot of space on the paper, and two, it's not a huge step. Because one of the things we saw already is 48 over 27 is 16/9. Also, powers of powers multiply. So we'd be multiplied our negative 1/2 and 4, giving us negative 2. Now we just need to apply that negative 2 to the top and bottom, telling us that we have 16 to the negative 2nd over 9 to the negative 2nd. Well, to make those exponents positive, I'd have to move the 9 from the bottom of the fraction to the top. Also, we'd have to move the 16 from the top to the bottom. 9 squared, 9 times 9 is 81. 16 squared is going to be 256. Telling us that 48 to the negative 1/2 divided by 27 to the negative 1/2, all to the 4th power, should reduce to 81 over 256. Well, this, for the most part, is a nice number. 48 over. So if I'd have decided to plug this into the 30xs, it would indeed tell me that it's 81 over 256. A lot of numbers there, but since it is a rational number and the numerator and denominator are not too big, it would do this for us. Let's go on and look at 15. Every term on top and bottom, the 2, 16, and 4 are all put to the 2/3 power. So essentially what we're using two properties in one, our power quotient, power of a product, and power of a quotient. We can pull that power out, leaving us with 2 times 16 over 4. Well, 2 times 16 is 32. 32 over 4 would be 8. Telling us that we have 8 to the 2/3 power. Eight to the 2/3 is indeed 4. And when you think about fractional exponents, the denominator tells me what root. It's a cubed root that we're looking at. What times itself? 3 times is 8. Well, that would be 2. So the cubed root of 8 is 2. We still have the square at the top. 2 squared is 4. Or if we did in the reverse order, 8 squared is 64. Cubed root of 64 is indeed 4. But that also means we could have plugged 15 into the calculator as it was from the beginning, and it would have told us that it was 4. Questions on 13, 14, or 15? So at this rate, we would just look at 16 and say 4 to the 1/2 times 4 to the negative 2/3, all to the negative 1/4. Okay, we can't use the calculator for this one here. We can use it to check and make sure our answer is correct. It is the same value, but we cannot use it to get the answer. We're going to have to actually use our property of exponents. Now, as we look inside those parentheses, both bases are the same. When we multiply like bases, we add the exponent. So we would be adding 1/2 and negative 3/2. Two ways we can do that fractional addition, because 1/2 plus 3/2 would be negative 2/2. 1 minus 3. Negative 2/2 is negative 1. Or we can say 1/2 plus negative 3/2 is indeed negative 1. Then we have our powers of powers. Powers of powers multiply. So we'd have negative 1 times 1, negative 1/4. Negative times a negative is a positive, and 1 times 1/4 is indeed 1/4. So we're saying that 16 is going to simplify 4 to 4 to the 1/4. Luckily for me, I do have it still entered here, and it gave us this here. And if I checked 4 to the 1/4, make sure I type that in. Yes. No, it is 4 to the 1/4. Ah, that's it right there. Yep, because it should be 3/2. There we go. Thank you. I'd have been staring at that for quite a bit longer, but it is still the same value. Thank you. Funny enough, it's actually also the same as 2 to the 1/2. Because 4 is 2 squared. So really we could say it's 2 to the 2/4, which is 2 to the 1/2. I would take either 2 to the 1/2 or 4 to the 1/4. Questions on 13 through 16? Questions on 17 through 20, one of these that y'all want to look at. Cube root of 6 times the cube root of 72 all over the cube root of 2. Now this one looks like, again, probably one that the calculator is going to throw us an irrational number at us. So we can use our properties of radicals to simplify. So the cube root of 6 times the cube root of 72, since they are the same radical, we can multiply what's inside. And unfortunately, the denominator is just the cube root of 2. There's nothing we can do to it. Now, from here, we can try to simplify any further, see if we can take the cube root of the top and bottom, or combine them and then simplify at the end. And the reason I say combine them is because if we look at the numerator and denominator, if we divide the product of 6 times 72 by 2, it will reduce. Because that's part of the issue here, is that we have the radical in the bottom of the fraction. Now, I'm specifically going to divide the 72 by 2 because it gives me 36. Now, normally we would look for prime factorizations, but realistically, we're looking for factors that can be put to the third power. And I mention that specifically because 36 is a perfect square. It is 6 squared. And if we're multiplying 6 by 6 squared, this is actually the cube root of 6 cubed, which is 6. All right, guys. Now, because it was a rational number, that means we could have actually typed this in the calculator from the get-go, and it would have actually told us it's 6. Now, the other option, instead of doing 6 squared, is we could have broke it into factors of 2 and 3, and it would have given us 2 to the third times 3 to the third, which would have been 2 times 3 once we took the cube root, which is still 6. Any other questions on 19? We can look at 18. Again, it's another division problem like 19. And since 486 is divisible by 2, I would put them together and say the fifth root of 486 divided by 2. 486 divided by 2 is 243. Now at this point here, we can do one of two things. We can check the calculator and see if 243 is a perfect fifth root or has a perfect fifth root, or we can factor tree. 243 is not divisible by 2, but it is divisible by 3. And it's 3 times 81. 81 is 3 times 27. 27 is 3 times 9. 9 is 3 times 3, so 1, 2, 3, 4, 5. 243 is 3 to the fifth. Now at this point here, we can rewrite the fifth root of 243 is the fifth root of 3 to the fifth power. Simplify out, telling us that it is 3. Or we can just say it's 3 because our fifth root is saying what number to the fifth power is 243? That number would indeed be 3. But that also tells us that, well, either calculator, if we plug the fifth root of 486 over the fifth root of 2, would have told us it's 3 also. Number 20. Might as well, 4th root of 8 times the 4th root of 8 is irrational number. So we're actually going to have to work these out. So if we did the factor tree for 8, 8 is the same as 2 to the third. So instead of looking at it as the 4th root of 8 to simplify, really we're looking at the 4th root of 2 to the third times the 4th root of 2 to the third. When we multiply like radicals, we can rewrite them as one radical with what's inside being multiplied. When we multiply like bases, we add the exponent. So really, we're looking at the 4th root of 2 to the 6th. And at this point, if I wanted to check and make sure, hey, do I still have the same value as our starting problem? We do. Questions on number 20 so far? At this point here, we cannot leave it as the 4th root of 2 to the 6th. Like I said, with variables, we cannot have a variable with an exponent bigger than the root because it can be reduced. Same thing is true with numbers. So the 4th root of 2 to the 6th, we're seeing how many groups of 4 2's would simplify out with this root. That would be one group. Because 2 to the 4th, the 4th root of 2 to the 4th. Really, we're saying the 4th root of 2 to the 4th times the 4th root of 2 squared. 4th root of 2 to the 4th is 2. 4th root of 2 squared does not reduce because there's not enough 2's in it to come fully out. So it tells us that we have 2 times the 4th root of 4. If you have a number in front of a radical that is not a square root, it's good to put that multiplication just to make sure it doesn't take that 2 with it. And we see that these are the same. Fourth root of 2 to the, or 4th root of 4 is square root of 2. 2 squared, 4. Any questions on 17 through 20? '21 through 24, which one do we want to look at? '22. So we went over these in class, and we talked about the fact for me to be able to solve this, we would multiply it by the conjugate of the denominator, which would be 3 in the square root of 5. We'd multiply it on top and bottom. However, the sign in the middle would change from minus to plus. On top, we would distribute through. Square root of 6 times the square root of 3 would be the square root of 18. Square root of 6 times 5 is going to be the square root of 30. On bottom, square root of 3 times square root of 3 would be the square root of 3 squared. Square root of 9, which would be 3. Square root of 3 times the square root of 5 would be the square root of 3 times 5, or square root of 15. Negative square root of 5 times 3 would be minus square root of 15. And negative square root of 5 times the square root of 5 would be this negative square root of 5 squared, or negative 5. If we combine like terms in the denominator, The square roots of 15s would go away. 3 minus 5 would give us negative 2. Now we do want to check our two radicals on top, make sure they don't reduce. Square root of 18 would reduce to 3 square roots of 2, because 9 times 2 is 18. Square root of 9 is 3. Can't take the square root of 2. However, square root of 30 is simplified because its main factors are 6 and 5, or 6, 3, 2. None of those have a square root. Now, if we wanted to, we can make that denominator positive by taking that negative out and multiplying it through the top, telling us that we have oh, yes, you're right. This should have been plus, not minus, because we multiplied by positive 5, not negative. That way, when we take that negative through, it's negative square root of 30 minus 3 square roots of 2 all over 2. And no, I didn't have to flip the square root of 30 and 3 square roots of 2. We could have written it the other way also. However, we learned another method for doing these here. (30xs) would also do these too. Which means really 21, 23, and 24, we can grab that calculator, throw it in, and it will tell us that each one respectively. Questions on 21 through 24? There will not be one like 25. Because really we would have to reduce, because we can rewrite 24 to the 1/3 as 8 times 3 to the 1/3. The 8 would come out 5 times 2, because 8 to the 1/3 is 2. Would give us 10 times 3 to the 1/3 minus 4 times 3 to the 1/3, which actually gives us 6 times 3 to the 1/3, if we were to work it out. Five cubed roots of 2 minus the cubed root of 128. This here is not going to reduce. We know it's going to give us a decimal answer for one reason and one primary reason. Cubed root of 2 is not a nice number. But for us to be able to simplify this, I need to be able to rewrite the cubed root of 128 as something times the cubed root of 2. Because that's the only way these are going to simplify. That's the only way these are combined, is if these radicals are the same. Now we can kind of cheat to it and say 128 divided by 2 is 64, and see, can I take the cubed root of 64, which is 4? Telling me that the cubed root of 128 is equivalent to 4 cubed roots of 2. We can verify that on the calculator. 4 times the cubed root of 2, and compare that to the cubed root of 128. We see that these are equivalent expressions, so that means that they are the same. And since we're able to rewrite these so they both have a cubed root, these are the same, so we will subtract the coefficients. 5 minus 4 is 1. So we have 1 cubed root of 2, or we would just say the cubed root of 2. Questions on these here? 27, 28, I would do the same thing for both of those. Those are square roots, yes? 30xs will do square roots for us very nicely, very easily. 27 square root of 6 plus 7 square root of 150, 62 square roots of 6. Same with 28. 9 square roots of 32 plus 7 square roots of 128, 92 square roots of 2. Last two we're going to look at today are these two here. And since we have variables, we're going to have to simplify them as far as possible by hand. We can't just do this in the calculator. When we divide like bases, we subtract the exponent. So n to the 18th divided by n squared would be n to the 18th minus 2. Numerator on top, or the exponent on top minus the exponent on bottom. So 18 minus 2. P, we would do the exact same thing. Exponent on top is 7. We're going to subtract from it the exponent on bottom, which is negative 1. 18 minus 2 is 16, telling us that we have n to the 16th. 7 minus negative 1, well, that's the same as 7 plus 1, telling us that we have p to the 8th. Anything to the 0 power is 1. It simplifies out. Now we need to take the 8th root of n to the 16 p to the 8th. Out of these two here, p is the nicer one because the 8th root of p to the 8th would be just p. And we can look at how many times can I take a group of 8 out of 16. How many times can I divide 16 by 8 evenly? And that would be twice. And since this divides completely evenly, there's no left over. It's just n squared. If there was any left over, if it was, say, n to the 17th, we would take 2 out. There would be 1 left over. So we'd have the 8th root of n left inside. Questions on this here? Different ways we can do 29. G to the 6, no matter what we do, is going to be on top because there's no g's on bottom, so nothing to simplify it with. However, we have h over h to the 7th. It's a little bit interesting because the bigger exponent is on bottom. So we could write it in the numerator as h to the 1 minus 7. 1 minus 7 is negative 6. We've got to move it back to the bottom of the fraction. However, when we divide like bases, we subtract the exponent. 7 minus 1 is 6. Since it's bigger on bottom, it's going to stay on bottom. At this point here, we're going to take the 6th root of both. Well, 6th root of g to the 6, 6 and the 6th root would simplify, giving us g. Same thing with h. So it's just g over h. Questions on any of this here? Now, the only thing we have left is solving, and I'm going to save that for tomorrow.